Good morning, everyone. Today we are going to talk about the shift from inverted index towards columnar vectorized execution search. This is an important topic for this conference as modern search workloads aren't just text retrieval anymore. They mix aggregations, vector search, real-time analytics, dashboards, and they all run on the same engine. We will dig into how this convergence is reshaping the execution model inside Lucene and OpenSearch. Let me start with a quick introduction about myself. My name is Ankit Jain, and I work as a principal software engineer on the AWS OpenSearch service team, leading large-scale performance and resiliency initiatives. I'm also an active maintainer for the OpenSearch and committer for Apache Lucene projects. For the last couple of years, I have been closely working on the aggregation execution path, and I have watched Lucene and OpenSearch evolve from per document iteration to bulk APIs to SIMD and now to streaming. We have a packed agenda for today. We'll start with some historical context, spend few minutes on storage versus execution, setting up the problem space. After that, we'll look at a couple of scenarios for skipping the data using inverted index, and also like how similar thing works with the columnar execution. And towards the end, we will spend some time looking at streaming and streaming using Apache Arrow. So yesterday, I think during the keynote, we were talking about a lot of history. I don't know, I think there were some people who had like more than 20 years working on open source. I don't know like if any of those people were there when Lucene was released as a text search engine, right, in 1999. In 2012, we added support for doc values, which is nothing but a columnar storage. In 2016, we had BKD trees, which is inverted index for numeric data. And in parallel, we were seeing some evolution in other search engine and analytics engine. We have TanTV in 2017 and QuickWit, which released on top of TanTV in 2018. The other category is analytics engine, like DuckDB in 2019, Velox in 2022, and Data Fusion in 24. While Lucene had columnar storage before most of these analytics engines even existed, the balance in the last 18 months, like we have introduced support for sparse indices, bulk collection APIs, skip index integration, and arrow flight. The balance between the row and the columnar storage is moving, and that's what this talk is about. So you might be wondering, if Lucene had columnar storage all along, why was the column path historically slow for analytics? Because storage and execution are two different things. Inverted indices answer which documents match. Doc values answer what value does this document have. Same data, two shapes, one for retrieval, one for scan. Both have been there for quite some time. Now, on the execution side, Lucene, remember, Lucene started as a text search engine, right? And it had a document at a time model, which was inherited from search. Iterate one document at a time, compute the score, and feed into the collector for top end documents or other collectors. This is the right shape for top end documents when every document needs to be scored. But this is not the right execution shape for an aggregation, where we are not ranking, we are rather grouping. We still pay one advance, one fetch, one virtual call per document. If you do that on a billion documents, that really adds up. DuckDB, Velox never paid this type of tax, batch oriented from day one. They never needed a per document score. So storage is already columnar. What needs to change is how Lucene flows data from through the engine. So we'll take example of a very quick analytics query. So this is like a NYC taxi data set, right, which a lot of you might be familiar with. And we will take a very simple data histogram aggregation over 12 months, which is a very common use case for log analytics. We just want to see the number of taxi rides on a per month basis, right? And when we used to run this aggregation on a large data set, so the result is only 12 count, right? 12 document count. But when we used to run this aggregation on a large data set, it used to take about 8 seconds. And when we looked at the flame graph closely, most of the time was going in the collection. And in the collection, we noticed that it was like, advancing to the doc value and then reading the doc value from disk. So initially, when we were thinking of optimizing this, we naturally started thinking like a search engineer. We were like, okay, how can we skip maximum data possible and compute these counts optimally? And that is the approach we came up with. So so here I think we are looking at a very simplistic model of numeric inverted index in Lucene, right? So we have something similar to BKD. So we have like instead of multiple children, we are just looking at two left and right, and all the data is stored on the leaf node similar to BKD, and this is like one-dimensional. I think Lucene supports up to 8 dimensions, but yeah, to keep it simple, we will look something like this. So now the initial idea was, okay, so Lucene has this optimized path for counting the number of matching documents in range query. Why can't we use that? And that is exactly what we did. So we created, for each month of our aggregation query, we created a filter and we computed the count for that filter. So like if you take one of those range query, it will start at the top of this tree and it will be able to, so there are only 3 cases. Either the whole subtree is fully inside, right? In which case you can just count from the node, the top node. The subtree might be fully outside, in which case the whole subtree can be skipped. And there might be some partial overlap, in which you will recurse further. And as you keep doing that, so the computation for our sample query here will look something like this. So all the leaves that are, all the nodes and leaves that are crossed out is something which got completely skipped because we were able to use this structure. When we applied this optimization and deployed it in OpenSearch, we were able to observe more than 50x improvement. So from 8 seconds, we got to about 200, 300 milliseconds just by doing this. While this optimization worked very well, there was a bit of an issue. So let's say if you are, instead of doing a monthly aggregation, you are doing a minutely aggregation for a day. Yeah, so I think there are like 40 minutes in a day. So the number of buckets is increasing. Now, if you are executing the same approach 40 times, it starts really adding up because these trees, like it is pretty shallow here, but on your actual production data set, it will be pretty deep. So every time you're starting from top, that cost is adding up. So that is where we, learning from the original implementation of count method in range query, we came up with this novel approach, multi-range traversal. So what it does is it uses the property that all these buckets that we want to compute the count for are in a sorted order, right? You can look at them in a sorted order and they are mutually exclusive. They are not overlapping. So if you place these buckets below the BKD, you can kind of think like they are partitioning the BKD into the corresponding buckets. So what you can do is you can again start from the first bucket, start from the top, and keep counting the documents until you get for the first bucket. And the moment you stop getting any results for the first bucket, you encounter a value which is larger than the max of first bucket, you know that the collection for that is done. In order traversal of BKD is always in a sorted order. So at that point, you can skip over to the next bucket. And if you keep doing that, the result looks something like this. So it's like very simple 2-pointer approach, right? And this ensures that even when you have like lot of buckets, you don't pay the penalty for iterating over the whole BKD. And once we implemented and deployed this approach, it resulted in up to 2x improvement even for the 50x case earlier, which becomes like more than 100x. And even for the minutely aggregations with many buckets, this performed really well. This is an optimization which was contributed back in Apache Lucene as well, uh, and yeah, it was very appreciated by the Lucene community. Now we looked at this example for inverted index, right? And this is like one of the question for some of the people who work more on the analytics engine like DuckDB and ClickHouse and others. And so, like, do you think that a perfect columnar engine, like even with all the SIMD, zone maps, concurrent scan, can match what BKD just did? Probably not. And I think that has to do with the cost shape, right? Even though those columnar engines are pretty fast, but they are actually visiting the document, right? It might be decoding a block, pop counting a bit set, skip on min-max metadata, but for blocks that intersect, it is reading or counting once per block. And so the total cost is some function of n, so it is still linear. But this BKD is able to answer that from the tree structure itself. So subtrees that fully cover or fully miss are answered from metadata. You don't need to go to the leaves. And cost is roughly log n cross buckets. And I mean, I think even though it says log n cross buckets, it is bounded by the tree size and the number of buckets, because you might end up skipping multiple buckets if there are no matches. Um, so one columnar technique is able to match this a bit, which is like pre-aggregation, something like star tree in indices in Pinot, open search star tree, because they are able to materialize the answer at index time. But even with star trees, you need to be able to decide, okay, these are the fields that you want to keep on top, right? And if you want to compute the aggregation on some other field, then you might have to again pay the penalty. But with this approach, it is completely flexible. So you might be able to change the granularity of your bucket. You might be able to do it on different fields. So it will be able to work for all of those. Now, we were able to get 100x improvement without visiting the documents, but we were not able to stop here. We were like thinking a lot from the search perspective, because we already had this inverted index in the form of BKT, and that biased the optimization towards a narrow shape. For example, if you are filtering, like, so our the query, if you remember, right, it is just saying, okay, all the data, give me an aggregation on monthly buckets. But now let us say if you have a filter as well. So you want to aggregate on the drop of date time, but you are filtering on the cost of your trip. So something like that will not work well with this technique, because there is no correlation between the two fields. So you actually need to visit the documents and make sure that the filter criteria is satisfied. Similarly, for sub-aggregations as well, right? If you want to, within each of the buckets, you want to compute, say, average cost, you need to actually visit the document for doing that. And also, I think Lucene has these immutable segments. So if you have deleted documents, those inverted indices are not accounting for that. So you have to either iterate through the deleted documents and course correct, or like not use this approach. So because like the real analytics workloads use multi-filter dashboard, metric sub-aggregation, high update indices, which don't fit the index-only shape. So that is when we decided, okay, we need to swap search to analytics, right? Now, columnar-only storage is naturally cheaper, right? Because it's like not only a query time win, but it is cheaper across the whole system. Without the inverted indices for analytics field like timestamp, metrics, status code, overall storage is much lower. Sparse index metadata can fit in RAM. Hot, like you can just check the meta. So you can have something like min max per 4K doc blocks, right? And which is like very small in size, probably few KBs per segment. And you can then use that metadata to skip over blocks efficiently without doing any IO. Vespa has built around this idea for some time now with attribute fields. Pinot, ClickHouse also follow a similar pattern. So There is also advantage of you are indexing less because you are not building additional inverted index data structure. You don't need to merge those during the flush time. It also results in better cache. Sequential primitives are what the prefetcher wants. So another reason this works very well is because it parallelizes really well. So while Lucene introduced intra-segment search for almost 2 years, but to enable true concurrency for large read-only segments, but it has not been able to make it default. And the reason is it is not easy to partition the work across different threads for inverted indices. For example, if you are filtering.
No, yeah. Can you talk?
I think so. Okay, yeah, that works. So when you are looking at inverted indices and you are querying across two fields, you are not able to conjunct that very well, right? Because both of them will operate independently. But when you are looking at columnar structure, that works really well because both the fields, the storage is sorted by the document ID. So you might be able to say, okay, I'm looking at the first block for both the fields, and based on the metadata, if I'm able to skip one of them, I can skip the other one as well. So um, think, yeah. And this is like one of the things that there is a Lucene issue which lists as a drawback for BKD, right? Uh, because like if you were to use inverted indices across multiple threads, you need to build the bit sets and whatnot, which is like a lot of duplicate work and memory as well. Now, this slide kind of shows the beauty of open source community, how strong collaboration and engagement again within the open source community can drive shared growth and success. A lot of these ideas were borrowed from other search analytics engine and implemented in Lucene. So like these are some of the common patterns that were observed across different engines. So like there is vectorized execution, sparse indices, pre-aggregation, sort-aware storage, arrow native execution. Like this is becoming more of a standard analytics engine playbook now. And there was another interesting pattern which came from Tantevi, which is like pop count. So pop count is a CPU instruction for population count. It is able to tell you number of set bits in a long variable in a single instruction. A number of set bits, sorry. Yeah. Uh, there is a post from Adrian on this, like why Tantevi is faster than Lucene, which covers this in a lot of detail. I recommend reading that if you're interested. And another thing is like the cross pollination works both ways. While Lucene picked this idea from Tantevi, it iterated on it and evolved it into something more. And the community even opened issue back in Tantevi that they can also leverage this technique for faceting, which Lucene is already doing. Now coming to the execution path, right? How do we escape the DAT tax? So conceptually very simple. You want to process the documents in batches, but the implications run very deep. For example, earlier it used to be for every document, fetch doc value, update the bucket. So it's like one virtual call per doc. Actually it's many because I think multiple of these calls are virtual. And it has been abstracted and implemented so many times in Lucene and OpenSearch that there are like more than 50 implementations of same APIs, right? So because of that, JIT is not able to inline, and there is no opportunity for auto vectorization. But after Lucene has iterated on this a lot, now for every block of n documents, you will bulk load the n values into a primitive array, run a tight inner loop, one virtual call per block, right? So number of virtual call goes down significantly, and inner loop becomes primitive array iteration, which is much more easily auto-vectorizable. So same shape, DuckDB and Velox have had from day one, right? DuckDB vectors at 2048 values, Velox has row vectors. So the change isn't about what you are computing. What we are computing is still the same. It's just how we are doing it differently. So this is again another view of the same thing, right? So it's just showing like some of those actual virtual calls that earlier Lucene was making for each document. So this values.advance is a doc values API, and it is a virtual call because you need to see which doc values implementation is being used, and then the actual fetch also is a virtual call. Now, in the new path, you are able to bulk load these values into an array, and you can count them in a tight loop. Bulk collection alone itself is a win because you are able to minimize the cost of virtual calls and allow for some auto vectorization. But when you are able to combine them with sparse indices, the gains really compound. So for every 4K doc block, you are able to store some pre-aggregated data like minimum, maximum values, sum, value count, etc., which has like minimum storage overhead, like roughly 0.1%. And then you are able to quickly make decisions on that. So when you get a bulk range of documents to collect from X to Y, so you are able to see which blocks it is overlapping with. So the idea is very similar to BKD. Either it will be completely outside that range, or it will be completely contained within the range in which we are able to use the aggregated result. And in some cases, it will overlap where you can either quickly iterate over them or use something like pop count when you are just interested in the number, the count of results, not the actual values. So when we combined this technique, we were able to observe 28x performance improvement on hourly aggregation with the filter on HTTP logs, right? So from 998 milliseconds, we were able to come down to 36 milliseconds, which is a really nice improvement. There were some other PRs as well for just adding the support or extension for bulk APIs introduced by Lucene in OpenSearch, which resulted in up to 40% improvement on high cardinality aggregation by removing just the virtual call overhead. So this is how the SIMD compute pipeline looks in case of batch collection. So bulk reads are able to give us flat primitive array, and SIMD turns those arrays into single instructions. So on a AVX 512 processor, 8 64-bit longs can be used per cycle. So if you are trying to count the number of documents on a 4K block of documents, this is able to just count it in very few instructions, which is like a very big win. And like once the inner loop is a loop over primitives like long array, with no virtual call, the JIT is able to vectorize that, and it is able to use the SIMD instructions. So we don't necessarily need to SIMD by hand, right? A lot of the bulk APIs automatically enable that. There are also like Lucene has integrated Panama vector APIs, which gives us explicit SIMD primitives. So already being used for vector search, it is coming to aggregation paths as well. This bulk read pattern and using vectorization isn't unique to aggregation. It's it is being used in some of the scoring queries as well, right? So there is this very nice blog by Adrian on this, how we were able to optimize the top K filter, uh, lo- score computing the scores for 128 doc postings block, right? And also make the top K filter branchless, which resulted in some really nice optimization. So I'll not spend like much time on that. This is something which can be read offline. And making these optimization in Lucene over the last couple of years has resulted in like really nice improvements across different type of benchmark. And like in 10.3, Lucene actually got on par with Tantivy, even though initially there was like a big difference. Although one thing I want to call out here is like you remember, right? Lucene took some ideas and iterated on it. So it was able to make ideas in Tantivy even better. Once Tantivy is able to implement those, it might be able to surpass the performance for Lucene again. So now there is an interesting question, right? Whether to use inverted or columnar or both, right? So I think these two approaches are complementary. They are not contradictory, right? If you have a high selectivity, small match fraction, or aggregation aligned with the index, inverted index wins. When you have low selectivity, like most documents are going to match, or there is a filter on a different field, then the aggregation column scan path wins. But the idea is overall same. Try to batch, try to skip, and try to vectorize. Different engines wire these ideas in their own way. For example, in Pinot, star tree plus columnar segments uh, in addition with inverted indices, Vespa streaming plus index plus attribute plus tensor. Radu can correct me if I'm wrong. Tantavi has like fast fields plus posting lists. OpenSearch chains them. It is like if star tree is available, it can use that for aggregation. Otherwise, it will try to use multi-range traversal. Then it can use skip index and then do the bulk collection. So the key takeaway here is Lucene was always hybrid. The job is just keeping, both columnar and inverted path sharp so that we are able to pick the best fit for our use case. So now we'll shift the focus from a single node to a cluster setting. While the implementation work that I cited was shipped in Lucene and OpenSearch, it was primarily focused on the single node execution model, right? And it applied likewise to both Lucene and OpenSearch. But this is like a very high level view of OpenSearch architecture on the search perspective, right? For every search request, the request lands on a coordinator node, and it's a scatter gather protocol. The coordinator will forward the search request to all the different shards for that index, and every OpenSearch shard is nothing but a Lucene index. So once like those indices execute that, those shards execute the query and send the results back to the coordinator, and coordinator aggregates those results and sends it back to the client. Now, if we walk through a real example using ClickBench, which is like one of the standard analytical database benchmark, having 100 million documents, 18 million unique URLs. So we are looking at a query that matches, 47K documents and asks for top 1,000 URLs by count. So this is like a very typical high cardinality aggregation use case. So the total execution time is about 500 milliseconds, and we actually break it down. Like the reading the doc values is almost like 140 milliseconds. This is the part, so the second part, collection. This is the part that we have been talking about and we have optimized, right? But you can see that, and the coordinator merge is just 5 milliseconds, almost free. Materialization, converting ordinals back to actual string keys, that takes about 34 milliseconds, which is again manageable. But top end selection is something which takes 320 milliseconds. That's like more than 64% of your total query time. So what is happening in top end selection? The shard is building a priority queue, sorting it, serializing it, all before anything is sent back to the coordinator. So the fully aggregated data is sitting on the data node for 320 milliseconds while the network and the coordinator are idle. This is where streaming aggregations come into play that we are building into OpenSearch. The idea is pretty straightforward. Instead of the shard accumulating a full result before sending anything, each individual Lucene segment emits partial result as soon as it finishes processing. These partial results stream over Apache Aeroflight to the coordinator, and the coordinator merges them incrementally as the batches arrive. Streaming aggregations naturally compose with concurrent search as well, because if you have like multiple segments being processed, they can all stream their partial results, and coordinator can keep aggregating those. So one of the important point here is the wire format, which is like Apache Aeroflight. Arrow is the same columnar representation that DuckDB, Data Fusion, and Velox already understand. So aggregation results don't need to be translated between formats. So if you even want to use another engine like Data Fusion on the coordinator side, you should be able to do that because the protocol is the same. Now, similar to multi-range traversal limitations, streaming approach comes with some trade-offs of its own. So materialization cost increases as materialization is done per segment using segment ordinals. So same keys might be materialized few times. So the net win on memory and latency to first byte is real, but the materialization isn't free. You pay it more often. Coordinator memory also grows significantly. The coordinator now sees all unique keys from all shards, not just the top n from each, right? So streaming queries can execute if they fit within the coordinator's memory, which is like some sort of constraint. But at the same time, you can have like different types of node as coordinator, which have like much larger memory because the resource requirement for coordinator and data node is much different now. Instead of paying the memory penalty on 10, 15, 20 data nodes, you are just able to do that on the coordinator. There is some implication on network bandwidth as well, because the same bucket can show up multiple times when streaming batches, right? So overall, the amount of data sent over the network is a bit more. But one thing that works well is like the top end results are more accurate, because by default OpenSearch, like if you are requesting n results, it will probably send 2n from each shard. It will assume that anything below the 2n is never going to make into the top n, which can result in some inaccurate results. Now, keeping these trade-offs in mind, streaming might not necessarily be the right choice always, right? If you have a high cardinality with bounded coordinator memory, then you probably don't want to take that. If you have low cardinality with expensive key materialization, again, the traditional path can be faster, which kind of means we need to choose something at the runtime. Now, these are some of the things that we are working on and are coming next, right? So we want to do some sort of adaptive query planning when it comes to streaming, when to use that, when not to use that. Then there is some block-based collection, right, which we are working in Lucene. You want to, so today, like the sparse indices in Lucene only support min-max, but you can have other aggregated information as well, like sum, value count, etc. Then there is this coordinated multi-field skip evaluation. This is a very powerful idea because you can, and this is something which like a lot of other analytics engine already use that. So if you are querying on 5 fields, you can iterate over the 5 fields concurrently. And if any of the field is skipping over a block, you can just skip for the other fields as well. So the different iterators are working in conjunction and keep skipping over the blocks efficiently. There is some work in including Panama vector API and aggregation paths as well. So even though like we have added these bulk APIs in the Lucene collectors, but you need to make sure that you are invoking those bulk APIs from the scorers, and a lot of work is happening on that, right? I have myself reviewed few PRs in last couple of weeks itself, and then once you invoke those bulk APIs, you want to make sure you are able to write the collection logic in a way that it is able to vectorize by using explicit vector APIs or maybe through auto vectorization. So yeah, I think this is all I had. I guess we have 5 minutes for Q&A. So thank you.
Do we have any questions from the audience? Okay.
Hey, hello, nice talk. I'm wondering what happens with the rights, are the rights now being penalized for building these new structures? Do you have some, let's say, benchmarks on this?
I think in a way you can say the rights are being penalized, but the penalty is very low, right? Because compared to something like inverted index, which are like more complex in nature, this is just, like very linear layout. And you are just storing the, for example, like some min max, which are like very low compute aggregate. So I don't think there should be any penalty on the indexing path. I haven't measured it myself, but I will estimate to be something less than 1 to 2%. There will be some implication on storage though, but again, it should be fairly low.
Yeah, thank you very much. Very nice talk. I have a question to the very first part with BKD trees. So actually in OpenSearch, if you have figured out some problems with that, because actually the code in the point range query for the counting only takes place when there are no deletions. Otherwise, it's counting the standard way. So I think for logging, it's not really a problem because you never delete something. But if one person just deletes one single document, then it gets something like, instead of a few hundred milliseconds, it's then again back to the 8 seconds. So have you seen issues coming from customers using that and suddenly deleting documents?
Yeah,
because you have to keep that in mind.
At least I don't remember seeing anything like that from our customers. But I think recently there was a PR merged in Lucene, which allows you to iterate over the deleted documents when the number of deleted documents is very low. I don't recall the name of the contributor. Yeah, but I think that is something which can be naturally followed up to plug into this. So when you have like very few deleted documents, you can just iterate over them and course correct your aggregation results. So I think the earlier the issue was because it was just live documents. You don't want to, if there are just one deleted document, to find that you have to go over all of them, right? Which is expensive. But if you have the support for just figuring out those deleted documents quickly, I think it becomes much more easier.
All right. If we don't have any more questions, thank you very much, Ankit.
Yeah. Thank you.